A 1-inch electrical conduit, a 6-inch drain pipe, 20-inch duct. And when you see those three things side by side and you ask, which one of these did the architect not plan for? It blows your mind. That ductopus, that octopus of a duct system where everything was coming off, this goes this way, this goes this way, this goes this way. It has the lowest resistance.
Alex Meaney is in the studio. He just got off of a plane. He is my HVAC design trainer. If you have not met him before, we've got a series of videos that this is going to be like a cap on. So this is all about manual D. Rule number one, just to get this straight, this is not a big deal within like all the math and calculations, but if you can put your HVAC system and all the ductwork inside your enclosure, you are already winning.
Especially an attic, right? If you're going to put it in a crawl space that's, well insulated, or if you're going to put it in an unconditioned basement, like those are slightly different animals. It still would be better to bring it inside the conditioned envelope and condition that crawl space. But yeah, if your choice is between an attic and getting it inside the conditioned envelope, that's a no-brainer. It's real hot up there, guys, right? Don't store candles in the attic, right? You know that one, right? Because they'll melt. Well, that's the environment you're putting the coldest air in the house in. By the way, you're protecting it with the least insulation. R8 is good duct insulation. Your attic insulation to keep the house protected from that heat is a minimum of R38. And go up north and it's R50. And we got a whopping R8 around our duct.
We have ACA Manual D.
Actual Manual D.
And we also have ASHRAE Fundamentals, Chapter 35, Duct Design, which I read years ago and then got more into this. So, give us the fundamentals that we need to be thinking about.
Well, actually, it's funny that you have those two next to each other. They're literally backwards from each other. With your ASHRAE Fundamentals method, you decide what you're going to size your ducts to. You just kind of pick a size. Not one size, but one size per duct. It's called a friction rate. And once you've decided that, you look at your system, the path of the longest run. You determine how much friction that creates. You do that. The friction rate tells me how much friction the duct creates per 100 feet. And the fittings will all have a pressure loss rating, otherwise known as a friction rating, for the amount of velocity going through there. And since you've decided what size your duct is going to be, you know what the velocity is, so you just add all those numbers up. All the friction numbers, the fittings, the duct, the filter, the coil, the grills, everything in the path. And then once you've added that all up, you pick a blower that can handle that. Because on the commercial side of things, which is generally what they use ASHRAE for, you have so many blower options, it's not even funny. You can change pulleys, you can change motors, you can change, there's all these different speeds. It's pretty easy if you need more power to just get it.
And I think that that's part of where my confusion with duct design kind of rooted, because I came to this as a HERS rater, which is why I think I'm going to be taking Manual J more seriously than somebody who comes from HVAC, is because if you're an enclosure specialist, you're like, okay, great, I get how to add up all the enclosure things. But so that's one problem, and I'm kind of astonished at how limited sometimes the choices are that we've got in residential.
Well, it's all about SEER rating, right? It's all about that efficiency stuff. We are basically everything is just hanging by the skin of its teeth SEER-wise, and the next blower size up causes you to lose basically about half a SEER point, half an ER point, and that's the difference. In the eyes of the manufacturers, that's the difference between somebody buying it and not. I don't know if that's actually true, but they've definitely convinced themselves of that. And when you look at the SEER minimums for the EER minimums for rebate programs, that half a SEER point can be really valuable. And so you are very, very limited to what your sizing criteria can be in terms of that blower. And so you work backward. You say, okay, this is the blower I've got. And maybe it's a high-end variable speed blower and it can handle up to this much. And that's as high as it's going to go. You still have to figure out whether your duct system is going to work with that. And so you go in the other direction. You lay the duct system out, and instead of doing everything in terms of friction, you do it in terms of length, right? You calculate the actual length of the duct run, and the fittings have what's called an equivalent length.
Which we're going to talk about today.
Yeah. Equivalent length is a normalized pressure loss. It is the amount of pressure loss in that fitting at 900 feet per minute and a friction rate of 0.08 converted into length of duct at 0.08 inches of pressure loss. Yeah, it's a very complicated thing. But really, it's a stand-in.
But we're not actually designing it for 900. 900 is the max that we're designing it for.
There's tons of wiggle room in the manual D.
Okay, and so this is the problem. This is why people like me who specialize in this and spend all my time doing this will then go and get more training, because like there is always deeper and deeper layers, which is why I hope you're subscribed to this channel. Now, let's back up for a second and talk about Manual D. Within Manual D, there is a worksheet. It's called the worksheet for Manual D. In order to get here, you need to start with Manual J, and after the Manual J, you get to the Manual S. So this is like the end of the line, and if you're accepting this as gospel, it means that the Manual S had to have been correct and the Manual J had to have been correct. That's a lot of assuming.
Yeah.
So he was like, great, use this and just take the map of what they're doing. And I wanted to understand how this worked, like in the software. It's a 5-step process. And what it says here is you got to, number 1, enter the blower data from the thing that you select. Number 2 is enter your component pressure losses. So if you have a high MERV filter, if you have things in the way of the ductwork, anything.
Coils and filters are the big ones.
You're adding a grill, pressure loss on the front end and the back end, return and supply, et cetera, et cetera. Then you calculate your available static pressure, which is the static pressure that's total, that's allowed on the sticker of the equipment, minus the things that we just took out by putting in that list. Then we have the total equivalent length, or a total effective length, which is the end of the longest return through the equipment out to the longest supply. And what is that? And then we calculate 1 friction rate from that. And then we apply that 1 friction rate to everything.
Well, when we do it by hand, both Elite and RightSoft are going to calculate a friction rate for each individual run.
Okay, so that's what makes, number 1, the software is already better.
Yep.
Because I swear to God, I did several of those. And now I'm like, that's why I'm getting all set up with RightSoft at this point, because like, I don't ever want to do that again. It's the worst job ever. So now I know why people don't do it by hand.
Yeah, it sucks.
Yeah.
It's not fun. So if you take it by the steps, right? So your step 1 is figuring out what your blower can do. That is not as like straightforward as you would think it is. Each blower has multiple speeds, unless it's a constant volume blower, which is otherwise known as a variable speed blower, which can deliver the airflow you want at a range of resistances by changing speeds on its own. And so you got to find the speed that you want to design at. Manual D recommends that you not use high speed. It's good to have access to a higher and a lower speed so that if something needs to be serviced and you decide you need more airflow or less airflow, you have that wiggle room. Plus, it's probably a wear and tear thing on the unit. When you're dealing with variable speed fans, they typically only give you the maximum static pressure, external static pressure that they're rated for. And there's not a ton of guidance. The Manual D says that I can use up to 70% of the maximum static.
For what?
So for your design. So if you have a carrier blower and it's rated at 1 inch of static, you can design at 0.7 or below. If it's a
That's the available? That's the total available?
That's the external, right? So that's your starting point.
Right.
Yeah, so they use the word available for that same number basically after you've removed all the stuff you can't do anything about, right? So static pressure is, the word pressure is used a lot of different ways to mean actually different things. When we say external static pressure, we basically mean fan power, right? When we say pressure loss, we mean friction, right? So one is the force of the fan, the other is the resistance to it.
It
right?
describes the machine versus describing the resistance.
Exactly. When we say static pressure to mean both things, and they actually are going in opposite directions. It makes it very confusing.
It is confusing.
Right?
And
so
we
the
have, by the way,
external
there's a video
pressure,
on how to do that testing, and
do
it
the
might
test,
make it a little clearer thinking about these kind of like analogies.
So you've got your the external static pressure rating of the blower, and you find out what it is at the speed that you want to use it at, and then once you have that number, you subtract all those filters and coils and whatnot. The Manual D gives you some gimmies for grills and balancing dampers, but the filter and the coil are 2 huge wild cards, like huge. They are all over the map. You have to look them up. It's one of the most common questions in my classes is what number can I just always use for this? Or is there some like MERV rating, airflow, blah, 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 equals this? No. One of the biggest reasons why actually is you can compare 2 filters with the same MERV rating, the same size filter, and the same width, and they'll actually have different surface areas of the media. If you look at the pleats inside of a filter, the wider those pleats are, the crappier the filter is in terms of airflow, because it's not as much surface area. The more zigzaggy the pleats get, meaning more pleats in that same space, means there's more surface area there, and air has an easier time finding its way through there.
But one kind of rule of thumb that I've heard from Aprilaire, which we like Aprilaire because they actually publish the table that says at different airflows, this is what it's going to resist, is that it's about 9 times the surface area for a 4-inch pleated on theirs as a 1-inch.
Yeah, and it's so, and I love Aprilaire too, specifically because they publish their data, right? You don't need a rule of thumb, right? Because, and the ones that publish data, if anybody is ever designing their own duct system, and you look at a filter table or data, and you notice that the pressure loss rating or the friction rating is the same all the way up and down the list, that is some shady stuff they're doing. What they're doing is saying, well, as long as you run the air through this filter at this speed, it will give you this pressure drop. And sometimes they publish it in a table, and I swear it's just to make it look more official, because it's the same number up and down the whole thing, right? So you can pretend to look something up. It's not really, if you're not putting exactly that much air through there, if you're not moving at exactly that velocity, that's not the pressure loss of that filter. And the fun thing about pressure loss, when you double your airflow, you don't double the resistance, you quadruple it pretty close. Because the velocity is linear, but the surface area is square.
And just a quick note, this is not a topic for this conversation, but I've got lots of clients who are now pumping makeup air for kitchen exhausts into the return, which is ballooning the amount of airflow. And so there are lots of instances where we might be doubling the airflow, for example, in a residential system.
Sort of.
Without having thought through the consequences.
Yeah, it's there's a lot of reasons why I hate that. Homeowners, I mean, you have a more educated homeowner base, but I mean, you're telling me that I cook dinner for an hour and it's uncomfortable in my bedroom when I go to bed 3 hours later, and those two things are related. It's really hard to wrap your head around as a homeowner. It's hard to connect those dots because that's exactly what will happen. I encourage people to do the math on how much 1,000 CFM of outside air is in terms of, depending on your climate, but usually in terms of humidity is the one. Even if you could size a dehumidifier for the amount of moisture you're bringing in, you would need more than one. You'd need commercial grade equipment. I've actually seen
one. Yeah, it's about as big as that couch over there.
Yeah.
It would be bigger than
commercial
the two of us
grade equipment, legitimately. It is an insane amount of humidity. So if you are a homeowner and you're considering having a oversized grill hood, my strong recommendation would be to plan it in the plans so that you can bring makeup air at the hood. The outside air should come in, touch the grill, and then leave, right? And that is the ideal circumstance for that. And because we choose these things so late in the game, there's never any room for it.
So let me get us back to, because we're we can make videos all day long, and he has to go and travel to his next training, which by the way, if you want more training on this stuff go to his website, which is meanhvac.com. Okay, now, we're talking about space and planning. And that's one of the main problems with HVAC coming in on a build, is that a lot of people, and this includes homeowners, if you're watching this and you have not thought about where you want to put your duct systems and where the central shaft that you're going to use to bring your duct work from the crawl space that's conditioned below, or a basement, up into the house, or from the attic down to the first floor is going to be, you need, that's the problem number one. So what consequences follow from not having room for that?
Well, I mean, when I give a presentation to builders, I have a slide that I use. And I've drawn 3 things to scale. One is a 1-inch electrical conduit, just a little circle, 1 inch. The other is a 6-inch drain pipe. And the third is a 20-inch duct. And when you see those 3 things side by side and you ask, which one of these did the architect not plan for? It blows your mind. Because that's the 20-inch thing is the one they didn't plan for. And by the way, the 20-inch thing is actually 24 inches because there's 2 inches of insulation all the way around it. And
which
that's
trade
the thing
comes
is
in
that,
after the other two.
yeah, it's the last thing we think of, and it's the largest dang thing we could be running through the building. It's a major problem for a lot of the styles of buildings that we build. So yeah, you do need to do some planning or be flexible, right? Maybe that closet has a little notch out in the corner somewhere for a duct to go, and oh well, I'm not going to be able to put even more crap in my closet. It's probably a godsend, right? It's probably doing you a favor. But yeah, there's a huge lack of planning for the literal most difficult thing to route through the house. And so it's a major problem.
And so in the final analysis, we're talking about, I like to advise people that one system is better, because if you start multiplying your systems, you need 2 ERVs now, one for each system. You need 2 dehumidifiers. If you want to distribute them throughout the house, you need 2 blah, blah, blah. Like it kind of goes on and on, 2 filters, etc. So it kind of multiplies at that point. But if you're trying to hide the ductwork and you don't want to see it, you might be forced to have 2, because the ducts are going to be smaller. You're going to have to take them all the way across the entire house, and you have to take a bunch of turns.
Yeah, and by the way, we haven't made our blowers that much more powerful. 400, it used to be 400 square feet per ton was the old terrible rule of thumb. Don't write that down, don't ever use it. But that was the old rule of thumb. And it was because we didn't insulate our buildings very well that it was, even when people did the calculations, they didn't make up that rule of thumb. It was not uncommon to have 400 or 500 square feet per ton. Now we're double or triple that with essentially the same blower. Like you literally are covering twice as much distance with the same blower power, which means for every CFM you're moving, you're probably needing a bigger duct than you used to use, right? So this used to fit, this used to work, this used to. Yeah, well we're not doing that anymore. Right, like we're covering a larger area with the same amount of airflow, or with less airflow, and it makes the job more difficult. It makes it harder to fit things places. It makes it harder just to make the duct design work, like literally make it so that it doesn't fail. We used to have open attics, right? Instead of these attic spaces that are just full of scissor truss. Framing members with these weird vaulted ceilings and stuff, and there's no direct path through there at all. Or a furnace or an air conditioner, air handler in the basement. They used to put that in the middle of the house, and now they stick it off in a corner.
By the garage.
And so the thing is about airflow, water flow, electron flow, pretty much any flow, is resistance adds in series, not in parallel. That means that when you daisy chain, when you go one after the other, after the other, after the other, you add that up. If you go in separate paths, you don't. So by putting something in the middle of the house, I cut my distances in half. By putting it on one end of the house, I double that distance. And by putting it in the corner, I over double that distance, because you actually get a lot more resistance from fittings than you do from length of duct. And so by putting it over in the corner, I'm adding like 3 elbows just to get to what used to be the main trunk line, which used to be half the damn distance. Yeah.
So straight duct is pretty easy. Let's take short. A 30-foot long section of duct is going to introduce the same amount of resistance as like one 90-degree elbow. One
good 90-degree elbow. You can have a 90-degree elbow that's 90 feet of straight line duct. They have those hard corners. 30 is a good day.
And so we've got this duct fitting poster from Southwork, which is a sheet metal manufacturer, and they have all of their fittings on this. It does not have all of the total equivalent lengths on it, which I might make that a project of my own, because I can't find a poster that has all of them with all of the actual.
The back of the manual D though.
Yeah, no, that's true. But you have to page through on what type you're looking at and all that stuff. I'd like to have it in one visual thing where you can actually look and compare. So, so elbows and fittings and all that stuff we want to try and minimize. Now here's the thing. In the softwares, you can select several different styles of duct, right? You can have flex duct with junctions. You can have trunk and branch.
Yep.
You can have, which one is the best, and which one is the most realistic?
Okay. So trunk and branch systems are easier to balance, generally speaking. They are less restrictive overall. However, some of those flex systems that have earned the bad name that they have, okay, You lived in that house, you went up in the attic, you looked, and it was the ductopus, right? It was just this spider of duct system with all these connections. That was probably not designed and probably not well installed. Flex duct does happen to be a little easier to do wrong, right? But
and also easier to do, though, in general.
oh yeah, easier to do.
Preferred.
Yep, and and it's also it's hard to screw up the wrap in a place like an attic, right? If you're wrapping
pre-insulated.
Yeah, exactly, pre-insulated. You have the connections to worry about, but like the length of the duct, you're generally not going to have like single points of sweat unless you're laying it down on top of the ceiling deck or something like that. And so it's often preferred in attic applications. Not that sheet metal is necessarily a bad thing in those applications. You just have to pay attention to what you're doing and do it well. But more parallel paths is less restrictive. And so that ductopus, that octopus of a duct system where everything was coming off, this goes this way, this goes this way, this goes this way, it has the lowest resistance, which is not something. It's that type of duct system is not often associated with craftsmanship, right? So you have a lot of people who are literally just slinging it and not particularly concerned with the quality of the installation, and so it's earned this bad name. It's not the product; it's the install. There are some people out there who are doing high-end homes, and they're quote-unquote value engineering them, right? They're taking a budget and saying, okay, we want to give you the best product we can. We don't want to skimp on the dehumidifier. That's a serious comfort concern. We want to have this dehumidifier. What if we did a good job of installing flex duct instead of doing sheet metal? It would be a little cheaper. And they're getting phenomenal results. Like they can be good if they're installed right. Speaking of that, the software program is called a variable friction rate. When you calculate the size of every single runout, when you have a system that has multiple runouts and you can size each of them for their own resistance, the performance is a lot better. You still probably I don't want to say probably. You still definitely have to balance it, but it comes out a lot closer to giving you the right amounts of airflow just because you have so many parallel paths.
So you can either add, and this is something that we calculated in our component pressure losses, a damper. So you put a grill on the return, grill on the supply, that's 0.03 plus 0.03. That's probably conservative. It's like a little high, probably.
No, it's in the
okay, cool.
It's not conservative.
And then we're adding in a damper that's just a manual damper in there. But now there are these opposable blade dampers built into the grill.
Yeah.
Called OBD grills.
Yep.
Is that like that seems to be preferred by, there's a buddy of mine named Stephen Reardon who has his own YouTube channel.
And they're more easily accessible. The homeowner can make their own adjustments and understand how it works. And the good ones work really well. But the blades are set back in the box and can control airflow fairly well. They can get a little loud if you choke them down really low. But yeah, and the advantage that they have actually is they can still maintain a slightly higher velocity when you're reducing that airflow. That's one of our big problems is like Southwark makes boots that come in certain sizes, and they probably would make any size combination you wanted, but the local supply houses are only ordering the common stuff. And so a 6-inch duct comes with basically 2, maybe 3 grill size options, because the boot that they make has a face that fits that size grill, or those 2 or maybe 3, and that's a big maybe, grill sizes. Well, you've got a crazy long duct system. You've got a whole lot less CFM for the same amount of space. I believe one of the times I was here, we were talking about having ceiling fans do some of the job of circulating air. But having good velocity at the grill is a useful thing. Well, if your ducts are getting bigger and your airflow is getting lower, that velocity is not coming, that air isn't coming out of that grill very fast.
So it just comes out and kind of pools in one area.
So the more you damper it down back in the duct, the slower it's coming out. If your damper is closer to the grill face, that air can come out a little bit faster, and can help for that reason.
But ceiling fans on low.
Huge fan.
There right now. Just easy.
Huge fan.
Okay, so let's do this. So once we know what our friction rate is, you use something called a ductulator, which I'm linking to an online version of this in the notes below. But the idea is that, and when I took this and I was helping some of the HVAC contractors who were working with my clients who hired me for the Manual J, they would give me the duct design and I'd say, great, use this friction rate. And then the idea is that they're going to take that friction rate and apply that to each of the ducts to do that kind of sizing.
Yep.
But does that actually happen in real life, do you think?
Yes, but we still teach a lot of people. We don't teach very many people the first part, the hard part. Look up the fan power, determine how much resistance there is in the mechanical space, determine the length of the duct, determine the number of fittings, the length of those fittings, add it all up, multiply by 100, divide by the total equivalent length, come up with a friction, and then come up with the friction rate.
Why the
all
friction rate
of those steps
is missing.
Right.
Yeah, right.
Because it's tribal knowledge, right? This is the way my dad did it, and the way his dad did it, and the way his dad did it. And if you take that ASHRAE book there, that's how they do it. They pick a friction rate, they design the system, they determine what the resistance will be, and they pick a fan to go with it. And so that was a very legitimate way to design a duct system for a very long time. And it's so easy that it just won't die. It won't go away. It doesn't really belong in the residential space. What a lot of people are doing is using 0.1 for everything or 0.08 for everything. And that might work some of the time, but it's not going to work every time. And if you're not doing the prerequisite calculations, it's not going to work so well. Now
in the tables in Manual D, it says that you want to stick between 0.06 and like 0.19 or something like that. But I understand why the high pressure would be a problem, just like you'd have a heart attack if it was your blood pressure. But why is lower? I thought we've talked about this before, and we said like there's no downside.
The math breaks. Well, there's two reasons. You can't oversize a duct. You have to get incredibly large to create, like there's a myth that if your duct gets too large, you're going to create what's called laminar flow. Laminar flow is, if you imagine the air moving in the bottom of the duct as like a river and then having a still volume of air sitting above that, that's what laminar flow would be. And the duct has to be insanely large for that to be the case. Very unlikely. But what does happen is, one, if you're outside the conditioned envelope, the larger the duct is, the larger your load is, because the larger the surface area is. And also, the colder the surface is able to get, because you have more, the air is going so slowly, it's spending a whole lot more time in contact with the surface of that duct, just dropping all of its heat off and bringing the temperature of that duct down, which can cause ducts to sweat. And so there is a bottom line limit. Also, the Manual D doesn't actually know what the pressure it's normalized, right? Now that I've been taught the language, I understand it better. The Manual D is using these equivalent length values. There's some on the back of this, for example. These are actual pressure loss values. You don't know what the pressure loss is unless you know how fast the air is moving through the duct. And we haven't gotten that far yet. We're calculating this before we know what the size is. So what are we doing here? How do we know what the pressure loss is going to be? We don't. We just take an average. Actually, they don't take an average. They take the worst case, or near about the worst case. They use 0.08 friction and 900 feet per minute, which, by the way, is also the maximum allowable velocity in a duct. If you go beyond that, it starts to get loud, and the math breaks. And as you start to go lower and lower and lower and go below 0.06, you're getting further and further away from that assumption about how much pressure loss is in that fitting. And so it just gets so far away that the math breaks again. Like, it just isn't going to work. Being too big is generally not a problem because you can always adjust that balancing damper. The more oversized you are, the more you're relying on that balancing damper to be the whole source of friction, and the harder it is to balance things. You're going to put this
because they're real touchy.
Yeah, you're going to be chasing your own tail a lot, trying to balance that
every
system.
time you change one thing in the system, just like any other system, it changes something else over here. So you have to constantly be retesting and then changing and then retesting over there.
So the closer you are to actual airflow numbers, the better.
I have a little duct design here, and I want to ask, because we've got a flex that looks like it takes a nice gentle curve.
Sure.
Does that count as nothing? Is that just free?
So there's a number in the Manual D for it. It's between 5 and 20 feet of equivalent length, depending on the velocity. When you do it like that in RightSoft, it doesn't penalize you for it. If you read, there's so much wiggle room in the Manual D. Everything is rated with the air moving through it at 900 feet per minute. The older versions of the Manual D used to have a little paragraph in it about the inherent factor of safety of the Manual D. And it's there for good reason, right? In personal opinion, not ACCA's opinion, no battle plan survives first contact with the enemy. Right? You draw it up like this on paper, it goes and it gets installed, maybe has to be modified a little bit, right? Because, man, I rarely see a building that is being framed the exact same way it is on the plan. And so there's number one. Number two, filters load, right? Filters get dirty and they prevent more and more airflow. And so you want to have a little more room for that so that, on day 2 of the install, you're already losing airflow beyond the point that you wanted it. And 3, when you balance a system, you create resistance. And you're adjusting the airflow to all the spaces to dial it in, but every time you close a damper, you're creating resistance. So if you design for this much and this much is all you can handle, you start closing dampers and now you're not getting enough airflow. And so the factor of safety, the wiggle room that's built in here or built in there, is intentional. But knowing that it's there in the hands of a skilled designer, you got a sweeping 90-degree bend in a duct. I got no problem with it. Now, there are a couple in here where they're doing it twice. Don't love that. We should probably, because that starts to add up, right? Resistance adds in series, one after the other, not in parallel.
Would it not be better to just come straight out of the end of this, or is that a no?
No. Coming straight out of the end of a duct.
Of a trunk.
Of a trunk, yeah. So you've got a main vessel, basically, and you come off the sides. The author of the Manual D, Hank Rotowski, would tell you that as long as you put a balancing damper in that takeoff, you could put one right at the end of the trunk. And that is considered blasphemy in the contractor world because if that damper is not properly adjusted and locked and gets jostled or slowly blows open from the resistance or whatever it is, that will have a tendency to be very overserved, right? Because air wants to continue on in a straight line, and then it hits the end of that duct and stops, and pressure builds and pushes it out. And it's a lot more complicated than that. It's actually the entire vessel's pressured. But still, it hits the end of that duct going pretty quick. And if there's a hole there, most of the air just wants to go. That air is lazy. Give it an easy path. It takes the easy path. And straight out the end is an easy path. So not a fan, and I understand why contractors are just like, nope, just don't do that ever. It sucks. Everything's gonna be bad about it. It's easier for it to be bad is a better way to put that.
Yeah.
It can be done, but I would not recommend it because now you're really relying very heavily on the installer to do a great job or a balancing team to do a great job of making sure that you don't have a problem with that. So coming off the side makes sense as long as they're avoiding too close to the end. I believe it's 2 diameters away from the end. So if it's a 6-inch duct, you want to have 12 inches beyond that point.
So I'd like to finish up
that last point
with our with a kind of general question, which is that I have been since we started training together, and I started trying to do things the Alex Meaney way, which is like, let's work with the contractor, the local installer. I have found myself basically in kind of a war with the HVAC industry. There are literally clients of mine who they show the Manual J around to the installers, and they're like, absolutely not. I would not do this. It's not gonna work, and you're gonna end up suing whoever it is and it's just like they're just not comfortable with math, I think is basically what it is. So, in the question of between whether we bring the guys up 15% at a time, or we slam them into full on science mode where I have to do the design because they're like, listen, I don't know anything about this. You're gonna have to tell me exactly what to do from beginning to end, and then I will do it, but I'm not taking the liability for this. What's the likelihood that they actually do a design like this perfectly, and you have the ability to test them, which is the benefit of having the numbers here on the piece of paper, right? And you can see the map and you can look at it in real life. But how do you think, where do we go from here? Because you're dealing with these guys, you're training them in real life.
It depends, right? I work with a lot of guys who wouldn't be working with you because they wouldn't need you.
Good.
Right?
Good. And that's the dream, by the way. That's my preference always.
I'm working with a lot of guys who are coming in to learn how to do this, or already kind of know how to do this and want to learn how to do it better.
Good.
And so there are a lot of HVAC contractors out there that do exactly this. I mean, I have been, since the last time I was on this show, which was during a 1-month business trip. I left my house the first week of January, and I didn't come home till the second week of February. I've been booked solid ever since, and I'm still going to be going into the second week of June. That's how many people in the HVAC contracting business want to learn how to do this better. It is not a small percent. Well, it's not a large percentage, but it's not a small number of contractors.
And spread out too.
Yeah, that is true. I go all over the country. But I will say, if you want to bring the contractor on board, I would probably start with the design and layout elements, right? Let's not talk sizing right off the bat, because that is going to be a trigger. Because all the contractors who are not familiar with this and don't do this, most of them, all they're thinking about is the very hot day of the year when the homeowner is going to call and complain it is not cool enough in here. That day is the hottest day of the year for everybody in the area. So anybody in their customer list that has systems that are not able to keep up, that phone is going to ring, and that's a nightmare scenario for that contractor. So they have a tendency to be a little gun shy about reducing the size of things. And too many people limp in. I don't like the 15% at a time. My class is 2 days, and 100% of the people who go, maybe not 100%, but majority of people who go to the class will tell me that was like drinking from a fire hose. Could you do this in 3? I'd love to do it in 3 days. I can't get people to show up. These are business owners, right? They don't have enough time to take 3 days out of their schedule, so I can't be in business if I have empty classrooms. But I still insist I won't break it up. I won't do just the load and the equipment selection and not show them duct design. Because if you do the load, you pick the equipment, and then you use 0.1 on this thing, it's not going to work. And we're going to turn around and we're going to blame the load, and we're going to drop the whole thing.
Science doesn't work.
And so what I recommend is, A, getting feedback on the layout, the design, where you want to put things, what style of things, et cetera, et cetera. And when it comes time to reveal the whole thing, right? Like, okay, this is the plan, the entire plan. One of the things I love to point out is, yep, this system is smaller than what you would have done. But look at the ductwork. For this 2-ton system that you would have put a 2.5 or a 3 in, would you ever attach these size ducts to a 2-ton system? No, those are way too big. No, they're not. See, what would have happened is you would have put in that 2.5, and then you would have put in smaller duct than a 2.5 needs these days, because filters are more restrictive and coils are more restrictive and the air has to go further, and all the reasons why we're not getting as much airflow as we used to. And that would cause the system to probably kind of work inefficiently and not for long. That is going to be a functional system. It's going to feel comfortable in the home because you've oversized and underducted. And one of them is a mistake in this direction, and the other is a mistake in this direction. And it ends up balancing out. And when you can sort of point to that and be like, yeah, no, I think actually if we didn't adjust, like this is smaller than you would normally use. I acknowledge that. To offset it, we have to use slightly larger duct to make it work. And just even having a concession to the fact that, no, this is, I realize this is a big change, and like all things being equal, this wouldn't work. But we're not doing all things being equal because we're not using the old crappy undersized number from this. We're going to adjust, and that's what's going to help it work.
And I'd say that the best way for anybody to learn how to do this, and I'm talking to the HVAC professionals right now, is to have a home that acts like this. Because once you live in a space like this, and I'm talking about my own homes at this point, it's like, great, this feels right. So I'm gonna make a pledge right now, because I like to give deadlines to myself in front of you, which is that I'm gonna work with Alex, and we're gonna develop I don't know how exactly it's gonna work, but I'm gonna have a database, a roster of contractors around the country who agree to take this science seriously and to work according to how the science is set up. I won't be able to QC them, but if a company says, yes, we are about this, we like it, I feel like that's the first step, because a lot of people will just be like, absolutely not. So I will have that up sometime soon. Will you help?
I can try.
Okay, so you guys, as you have questions, post them below. We'll keep this series going with Alex. Again, go to meanhvac.com. Thank you very much for
My pleasure as always.
Like and subscribe. Tune in next time.